Right, welcome to part 2 of equilibrium. So hopefully you've watched part number 1, and if you haven't, here's a very quick summary of what I mentioned. So I mentioned that if a rigid body is in equilibrium, the resultant force in any direction is 0. And what I said is, most importantly in this chapter, that's going to mean that upwards forces are equal to downwards forces. The second thing I said is that if something's in equilibrium, the resultant moment about any point is 0. And I said the way we should think about that is that clockwise moments are equal to anti-clockwise moments. I also gave a brief definition of a uniform rod and what it actually means. So it means the weight of the rod acts at its midpoint. And I also said that when we take moments, always try to take moments from a support if possible. And I explained in the last video that it helps you to eliminate some of the forces. So super useful to do that. Now, the examples here will be a little bit more tricky than they were in the previous video. So let's get into it. So here's our first one. In the following diagram, a uniform beam AB, so we should label the start of the rod as A and the end as B. It's got a mass of 80 kilograms, a length of 7 meters, and it rests horizontally on two supports at A and at C. So if this support is A, that means this support must be C. Now remember, if the rod is resting on the supports are pushing upwards on the rod. So we need to put in reaction forces at A and a reaction force at C. Now we've also got some distances that they've given to us so far in the question. So they told us AC is 5 meters. So we could fill in that distance there. It's 5 meters. We know the beam is uniform, meaning that its weight acts directly in the middle. And because it's 7.5 meters, that means 3.5 meters is where the weight is acting. Now, they have given us mass, so don't be tricked here, because we've got to turn mass into weight. And weight is equal to mass times gravity. So for us here, weight is going to be 80g. So we need to put 80g at 3.5 meters. So I'm going to say that's about here, 80g. And if that's 3.5 meters, that means this distance on the right should be 1.5 meters. And now what I can do is get rid of that 5 meters. That's not very useful to me anymore. So let's get rid of that and that there. Okay, there we go. So I think that's all the info we can put on so far. Let's continue reading. So an absolute legend, I wonder who that is, of mass 70 kilograms stands on the beam at E, such that the magnitude of the reaction at C is twice the reaction at A. So let's just think about what we've been told here. So we're told the reaction at C is twice the reaction at A. So what we can say is reaction at C is equal to 2 lots of the reaction at A. Now what that means to me is that this is pushing up with a greater force than A, which means that something heavy is probably near to it. So I'm going to say that this person is standing quite near to C. So maybe over there. I don't actually know, but I'm just going to guess it's there for now. And we don't know the distance that they're standing away from A, so we should fill this distance in with X. I mean, that seems pretty good. Now we also know this is 3.5 meters, this is 1.5 meters, and the whole rod was obviously 7, so we need this to total 7, which means this excess bit on the end here must be 2 meters. And there we go. I think that's, most of the info there. One more thing to fill in is, because we've got the mass of this person, we need to fill in his weight again, right? So don't be fooled here. This is going to be 70g going downwards, okay? Not just 70. And that's our diagram done, completed. I think we're ready to actually get started now. So the routine from last time was, we're going to start with upwards forces equals downwards forces. So I'm going to say I'm looking upwards and downwards. And upwards we've got RA and RC, and downwards we've got 80g and 70g. So I'm going to say RA plus RC is equal to 80g plus 70g. And so I can say RA plus RC equals 150g. Now, we were given some information about the reaction forces. We were told RC is just equal to 2 lots of RA. So what I want to do now is do some substitution. Because instead of writing RC here, I can substitute that for 2RA. Which means I've got RA plus 2RA is equal to 150g. Therefore, I can say 3RA is 150g, which means RA is just 50g. And now I can take that and substitute it back into this equation over here, because I know RA and RC together are 150. So that means that 50G plus RC equals 150G, which means that RC, we've got 100G as our reaction force. Okay, this is perfect. Let's fill this in on our diagram. So RA, we've got 50G, so I'll write it on top of it, 50G. And for RC, we've got 100G, so 100G on top of RC. There we go, fantastic. So this is great. Now, the other thing we should do is take moments now, right? That's what we did. And where should we take moments about? Well, I'm going to take moments about A. And the reason I'm taking moments about A is because I want to find the distance A to E, which is where I'm standing. And that distance is X. So it makes sense to take it from A. So if we take moments about A, the forces that we need to consider are going to be ATG, because there's a perpendicular distance to ATG. We need to also consider that force RC, and we also need to consider the weight of the person as well. So there we go. Now, which ones of these forces are going clockwise? So we can see that 80G and 70G are going clockwise. And that means the 100G is going anti-clockwise. So let's just set up clockwise is equal to anti-clockwise. And now looking at the clockwise direction, that'll be 80G times by the distance away from the pivot, which is 3.5. So we're doing 3.5 times by 80, plus we've got to include this 70G force as well. So what's that distance? Well, we don't know, it's X, right? So we're going to say X times 70G, so that's maybe just 70GX. And now in the anti-clockwise direction, we're going to be looking at this force here, 100G. And the distance away from there is 3.5 plus 1.5, that's 5 meters in total. So we can just say 5 times by 100G. There we go. So we've got a nice equation set up here. Let's try and solve it. So 3.5 times by 80 is 240 plus 40. I think that's 280. Oh, that should be a G on there. Let's not forget that. So 280G plus 70GX equals 500G. So that's what we've got so far. Send that 280G to the other side. So we've got 70GX is equal to 220 G's. Cancel out the G on both sides and then divide across by 70. So we've got 220 over 70. Cancel out those as well. So we've got, let's just carry this one up here. We've got X is equal to 22 over 7, which if we turn that into a mixed number is going to be, let's say 3 and a 7th. And now X was referring to a distance, right? So make sure you put meters on the end of that. And so what it tells me is that this person was in fact standing 3 and a 7th meters away from A. So in fact, not here. I mean, this person was in fact standing, what, 3 and a 7th? Maybe about here somewhere, in fact. So even though they were standing there, they were still closer to C than they were to A. So there we go. Main thing to take away from that is even though we don't know where you're standing, it still isn't really going to affect our calculations. It will come out correct in the end anyway. Now, one more example. This time we've got a bit of a slope, right? So something a bit different. Let's have a little read and see what we've got. So in the following diagram, a uniform rod beam, AB. So A down the bottom, B at the top. It's got a mass of 10 kilograms. So remember, we're going to be using 10G. And length 5 meters. It's hinged at A, so there's a hinge down here. Now at a hinge, the forces tend to be a little bit tricky at a hinge. They can act upwards, they can act sideways. So I'm just going to put this for now. All right, I don't know which way the forces are acting at the hinge. And it's held in equilibrium by a force Y acting perpendicular to the beam at B. So there's B, and this force here is Y. So let's label it as Y. And it's acting perpendicular, which is great news. Because we're not going to need to find any distances. Hopefully we're just given the distance of the rod, which we are given. It's 5 meters. So let's just fill some of this info in on the diagram. So we know that the total distance from top to bottom of this beam is 5 meters. And it's modeled as a uniform beam, which means its weight is acting at the middle. So let's say this is the middle here, and I'm going to draw that going downwards as 10g. The distance from here to here now would be 2.5 meters because it's halfway. We need to fill in some angles as well. So we were told that the beam is angled at 40 degrees to the horizontal. So that there is going to be 40 degrees. So hopefully you can see that. That's all good. I think that's about it. Yeah, that's all we can do really. So with this one, because it's on a slope, I think what we're going to do is we're going to go straight in and we're going to look at moments, right? So watch what happens when you look at these. We're going to take moments about A again. So down here at this point. Now, remember, if you watched that first video, if we're taking moments about this point, what we said is we can disregard any of the forces acting at this point. And that's because the distance to these forces is 0. So it means that, if you're thinking about our formula, force times perpendicular distance, the perpendicular distance is 0. So we can get rid of those forces completely. So the only forces that we're actually looking at are the 10g and this force y. And now what we need to do is calculate the value of y. So this is perfect. I think we should start by taking moments at A. So if we take moments at A, hopefully you can see the 10g is going to be is going to have a clockwise moment. And the force up here, y, is going to have an anti-clockwise moment. So I can't use this distance 2.5. Why not? Because it's not perpendicular, right? This angle here is not 90. So what we need to do first of all is actually find the perpendicular distance from A to this force, which we can get, along here. So let me just draw that in. Let's do it in green. So we need to find this distance down the bottom of that triangle, because that there is the perpendicular distance to the force 10g. So maybe let's create a little triangle outside of that. Let's do it in the corner over here. And we know this is 40. We're looking for this, and we know the length of the hypotenuse is 2.5 meters. So if we label this time, that's our opposite. This is our adjacent, and this is in fact hypotenuse. So what are we looking for this time? We need to use the Cos ratio. So cos 40 is equal to the adjacent over the hypotenuse. And therefore our hypotenuse is 2.5. Let's fill that in. So 2.5 times that across, and we've got 2.5 cos 40 equals the adjacent, which was x. So the distance down here is 2.5 cos 40 meters. And now that we've got that, we can calculate the moment, right? So let's set up clockwise is equal to anti-clockwise again. And now clockwise, we worked out our distance, and we've got our force here, 10g. So we just multiply those together. So it's going to be 2.5 cos 40 times by 10g equals to the anti-clockwise moment. Now that is perpendicular to that force. So this is great. I don't need to do any work there. That's just going to be 5 meters and times by y. So I'm just going to put 5y. And simplifying this bit down a bit, 10 times 2.5, we can make that 25g cos 40 is equal to 5y. And if we divide that across, we'll have 5g cos 40 is equal to y. So punch that in the calculator, see what you get. I think I've worked it out somewhere. No, maybe I haven't. Okay, let me type it in real quickly. Bear with me. 5 times 9.8 cos 40. And that should come out as 37.5 newtons to 3 significant figures. Okay, there you go. So there's a couple of examples done. A bit more tricky than we saw last time. And now it's your go. Okay, so you've got one here. I'll pause the video and then we'll have a look over it in a couple of seconds. Okay, whoa, hold up. Let's get through this, right? So you've got A and B as our uniform beam. We told that it's resting on a support at C, so this must be C. We've then got reaction forces RC and RA. We're told A to C is 11 meters. So that there is 11 meters. And because it's uniform, remember, uniform meaning its weight is acting in the middle. So we need to take a force of 60G and put it bang in the middle. So we're going to go with 60G. I hope you put 60G, not just 60, right? Because that's in the middle, that's supposedly going to be 7 meters, which means this would need to be 4 meters in order to make 11. And then the bit on the end here must be 3 meters, because in total we need the length to be 14 meters. So there we go. That's quite a bit of info there. We've now got the man, 90 kilograms, right, standing at E. And if we look carefully what it says that the magnitude of the reaction at C is 8 times the reaction at A. And to me, that means that this man must be standing somewhere near to C. So I'm just going to put him there for now, right? We don't know the distance, so I'm just going to call that distance X. And let's not forget his weight, which is 90G. There we go. So I think that's all the info. The place he's standing is called E, and we're all set to go. Now, we were told the reaction at C is 8 times the reaction at A. So hopefully you've gone with RC is equal to 8 lots of RA. And then we can look upwards and downwards. So upwards and downwards, we've got RA plus RC is equal to, well, 60G plus 90G, that's the downwards forces. So we'll just say 150G. Next thing, let's do some substitution, right? Because we were told that RC is 8RA. So we can say RA plus 8 lots of RA is equal to 150G. And that means 9 lots of RA is 150G. Divide that 9 across to the other side. RA is 150G over 9, which simplifies to, you can divide both of those by 3. So we've got 50G over 3. There we go. So 50 over 3G. Perfect. And now what we can do is sub that back into the top one, right up here if you wanted to work out RC, because we're told RC is just 8 lots of RA. So 8 lots of 50 over 3G. That means RC is going to be 400 over 3G. And there we go. So we've got RC, we've got R8. Let's fill it in on the diagram. So here, 50 over 3G. And for RC, a bit bigger, obviously, 400 over 3G. And there we go. We've got those. Now, the next thing we need to do is take some moments, right? Moments about somewhere. Where are we going to take moments about? Well, hopefully from A. So let's just write this down here. Moments about A. Now, if we're looking at moments about A, we'll need to consider, well, that force there, that force there, and that force there. So those are all perpendicular and coming off our beam over there. So let's start with, if you remember, clockwise is equal to anti-clockwise. You've got that there. Now our clockwise moments, 60G and 90G are both going to create clockwise moments. So we'll need to do 7 times by 60G. Plus, now we don't know the distance that the man is standing, so let's just call it X. So that's going to be 90GX. Now, looking at the anti-clockwise moment, that's going to be caused by the 400 over 3G, which is the reaction at C. So that's just going to be 400 over 3G multiplied by, and the distance that is 11, isn't it? So there we go. Now simplify this down just a touch. That's going to be 420G plus 90GX is equal to, oh goodness me, let's multiply that real quickly. I think that would be 4,400G over 3, I think on that side. Double check that, hopefully it's correct. Next thing, take that away, take the 420G to the other side. I can't do that in my head. Let's just quickly tap that in. 4400 divide by 3. Take away 420, leaves us with 3140 over 3G. We can strike out our G's from both sides, and then to find X, we just need to divide that by 90, and then we're there. So divide by 90, and that comes out to 3 sig figs as 11.6, I believe. So 11.6 meters. And if you think about it, I mean, from there to there is 11. So, he's just a bit past that. So, I think almost guessed right, to be honest, just after there. So hopefully you've got that for the first question. If you've got it, well done. That's amazing. Right, next one. So now we've got one on a slope. Just pause the video again real quick and have a go. And we'll catch up in a couple of seconds. Okay, right, let's go. So uniform beam again, A and B. It's got a weight of W, right? And that's acting at the middle, right? So here, and we got W this time. Not WG, W, okay? So don't be fooled there. We've got an angle of 25 degrees. It's got a length of 4 meters, so we know that this has got to be 2 meters, this has got to be 2 meters. Now at A, we've got a hinge, and if you remember, what I said is that a hinge, the forces can act in like all directions, it's all mad. But basically, what we're going to do is if we take moments about there again, we can ignore those forces. So make sure you remember that top tip. Okay, and then what else? We've got a force at the top here, which is 13 newtons. And that's perpendicular, so that's great, great news. Let me put in a 90-degree angle there. And I think we're all set to go again. Perfect. So if you remember what I said, we're going to take moments, right? And we're going to take moments about this point at A. So moments at A. Now, the forces that we need to consider are going to be the W and this 13 newtons up the top. But obviously for the W, that distance there is not the perpendicular distance. Remember, we've got to draw a triangle, right? So we're looking for that distance along there. So we can take maybe a little bit of space on the side of the page. We'll go up here, make a quick drawing. That's 25 degrees. This is 2 meters. That's a right angle. And we're looking for this here, right? So label the triangle, that's your opposite, adjacent, and this one's a hypotenuse. And therefore, we're going to need the cos ratio. So cos 25 is equal to, and that's going to be x over 2. Send that 2 across. 2 cos 25 is equal to x. And there we go, we've got our distance. That's our perpendicular distance, right? So we'll go clockwise equals, I'm just going to put anti for now, there we go. So clockwise times anti. Now in the clockwise direction, that's going to be w times by 2 cos 25. That seems good. And equals anti-clockwise. Now with anti-clockwise, that's 4 meters away, and we've got 13, right? So it's just going to be 4 times by 13. So we've got w, or 2w if you like, cos 25 equals 40, 52. And then divide that across, w is going to equal 52 over 2 cos 25. So punch that all into the calculator, and I think that is supposed to come out as about 28.7 newtons, and that again is to 3 significant figures. So well done if you've got that. If not, have a look back through the video, see what you've missed out, etc. And see if you find out where it's all gone wrong. Now, thanks for watching. If you've learned something, give us a like and subscribe for more. And hopefully I'll catch you in the next equilibrium video. There's one more to go. So some more tricky examples there, right? So if you're not quite so sure with it yet, check out that video, and hopefully by the end of it, you'll be all good.